Hello juniors, today we're going to see electronic assignment number 13 about expectation. This is the second electronic assignment corresponding to the last chapter of the book. If you remember from last class, we have seen the concept of random variables, and where the most important thing that you had to remember was how to build a probability distribution, the probability distribution table, and the two properties of probabilities in general, which are that the sum of all of the probabilities in a specific universe is always equal to 1, and that a probability can never be a number less than 0 or greater than 1. That is, it is always between 0 and 1. Okay, so today we're going to see the concept of expectation. It says, determine the probability distribution of random variables, find the expected value of a random variable. Okay, so what is expectation? It says, the mean or expected value of a random variable x is the average value that we should expect for x over many trials of the experiment. Okay, then it says, the mean or expected value of a random variable is represented by e of x. Okay, so this is the symbology for expected value of a random variable x. So here it says, expectation is actually the mean of the underlying distribution, the parent population. It is often denoted by mu. This is a Greek letter that is read as mu. Okay, so let's do a short investigation to see what this is about. You'll see that it's a very simple concept. It says, two dice are rolled together and the difference d between the scores on the dice is noted. Copy and complete the probability distribution for d. Okay, so we're interested in the difference between the results in both dices. So to do that, I have already built this sample space diagram where we're going to fill in the information, right? These are the outcomes for dice number 1. These are the outcomes for dice number 2. So we're going to record the difference between the outcomes. So 1 minus 1 is 0. All of this diagonal must be 0 because we're getting the same result on the two dices. And then 2 minus 1 is 1. Then this is 2, 3, 4, 5. Then this is 1, 2, 3, 4, and 5. Then this would be 1, 2, 3, 4. 1, 1, 2, 3. 2, 1, 1, 2. 3, 2, 1, and 1. And finally 4, 3, 2, 1. Okay, so this is our sample space diagram. So with this information, we're going to complete the probability distribution. What is the probability of obtaining 0? Remember, our universe in this case is 36. There are 36 different possible outcomes, 6 by 6. So the number of zeros are 1, 2, 3, 4, 5, and 6, right? So the probability of getting a 0 is 6 out of 36. 6 out of 36. Then the probability of getting a 2, that's 1, 2, 3, 4, 5, 6, 7, 8. So it's 8 out of 36, right? 8 out of 36. Probability of getting a 3, 1, 2, 3, 4, 5, 6. 6 out of 36. 6 out of 36. Remember, I'm not simplifying this for a reason, okay? We're going to see that in a second. 4 is 1, 2, 3, 4. So 4 out of 36. And finally, for number 5, we should get what's remaining, 2 out of 36. 2 out of 36. You see that if I add up all of these fractions, 6 plus 10, 16, plus 8 is 26, plus 6 is 32, 32 plus 2, that's 30, sorry, I missed something, 26, 16 plus 8 is 24, and then this is 30, 34, sorry, I'm missing something here. Okay, never mind, but the addition should always be equal to 1. 16 plus 8, that's 24. 24 plus 6, that's 30. 30 plus 4, that's... yes. 34. 34 plus 2, that's 36 out of 36, so we get 1. Perfect. So it says, This experiment is repeated 36 times. Copy and complete the following table to show the expected number of obtaining each of the different values of D. Okay, so if you take a look at this probability, the probability of obtaining 0 is 6 out of 36. If you want to read it in a different way, this means that if I throw the dice 36 times, I would expect that 6 of those times I would get a 0, right? That's what the probability means. So if I do this 36 times, the only thing I need to do is multiply all of these probabilities by 36. Okay, so the expected number of zeros I should get in 36 throws is of 6, right? The expected number for 1 is 10. The expected number for 2 would be 8, then 6, 4, and 2. Okay, that's what the expected value is about. Here it says you may find it helpful to draw a sample space diagram. Okay, we already did that. Number 3, it says, calculate the mean of this frequency distribution. What will happen if I calculate the mean of this frequency distribution? Do you remember how to calculate mean? In order to calculate mean, I need to multiply the value, or in this case the difference, times the frequency, right? Value times frequency, difference times frequency, and divide all of that by the total amount of throws, which in this case is 36. So I'm going to do that here. We're going to say that the mean is equal to 0 times 6, 0 times 6, plus 1 times 10, plus 2 times 8, plus 3 times 6, plus 4 times 4, plus 5 times 2. And all of this is being divided by 36, right? Because we do 36 throws in total. If you make this division using your calculator, you should get a value of 35 over 18, which is approximately 1.94, okay? Then we're gonna analyze the meaning of this value. For number 4, it says, the original experiment is now repeated 100 times. Repeat the questions 2 and 3 for this situation. Okay, so we have the probability, right? So if I throw this 100 times, now I will have to multiply each of these probabilities by 100 instead of by 36, okay? So that's exactly what I'm going to do. I'm going to multiply all of this by 100. 6 over 36 times 100, this gives us 150 over 9. 8 over 36 times 100, that's 200 over 9. Then 6 over 36 times 100, that's again 150 over 9. Then 4 over 36 times 100, that's 100 over 9. And finally, 2 over 36 times 100, that's 50 over 9. If you add up all of this, you should get 1 over 1. Okay, sorry, no, not 1 over 1. We're talking about expected frequency here. So we expect that 150 over 9 times we would get a difference of 0, okay? So, what if I calculate now the new mean of this? To calculate the mean, I would do the same process, right? I would do 0 times 150 over 9 plus 1 times 250 over 9 plus 2 times 200 over 9 plus 3 times 150 over 9 plus 4 times 100 over 9 and finally plus 5 times 50 over 9. If you do and all of this is being divided by the total amount of throws, which in this case is 100. If you calculate this mean, you would get this result. You can do this in your calculator and you would get 35 over 18, which if you see is exactly the same result we got here, right? It's exactly the same result. Let me frame this and frame this. So what do you notice? The first thing is that the mean is the same, right? So we're going to write here, mean is the same. And what does this mean? For question 6, it says, what would the mean be if the experiment were repeated 10 times, 1,000 times, or just once? Well, since by looking at the previous results, we can conclude that the the mean would stay the same, right? Same mean. So that means that the expected value of a specific value, in this case the difference, for example, the expected value for getting a difference of 0 is independent of the number of throws I do, right? It only depends on the probability of obtaining that specific value, right? And that's what expected value is about. It says, we would expect the mean to be the same in each case. Therefore, we can find the mean or expected value of the random variable d by just multiplying each value of d by its respective probability. The equivalent of conducting the experiment just once, okay? So that's what this is about. The expected value of a random variable x is, and this is expected value, is equal to the sum of the product of each variable times its probability, okay? So it's basically this times this, plus this times this, plus this times this, plus this times this. We multiply and add up all of those terms and we get the expected value, okay? That's the concept of expected value. So let's do the example, two examples in order to ground this concept. It says, what is the expected value of x? So if I want to find the expected value of x, the only thing I need to do is, now that I know the concept, is to multiply each of the values of x by its probability and then add up all of the results, okay? So this is 0 times 125 over 216 plus 1 times 25 over 72 plus 2 times 5 over 72 plus 3 times 1 over 216. If you perform this using your calculators, you should get an expected value of 0.5 or 1/2. So this is 1/2, which is the same as saying 0.5. Okay, one thing that I forgot to discuss about in the investigation is, what does this value mean? What does the 1.94 mean? In this particular situation, we're talking about the difference in the dice, right? This 1.94 that we get as a mean means that if I perform this experiment multiple times, let's say 1,000 times, then the mean difference, the average difference that I will get by doing the experiment multiple times would be 1.94, okay? That's the meaning of the expected value. So same situation here. If I repeat this process multiple times, this is the example of getting a 6 by throwing a dice 3 times, okay? The same probability distribution. That means that if I throw, if I throw the dice 3 times, the expected value of 6s that I would get is 0.5, okay? So by throwing the dice 3 times, I would expect getting a 6 0.5 times out of the 3 times, okay? I know it doesn't sound very logical, but it works that way. Okay, that is the expected value then. Now let's see an exam style question. You'll see that this is not very difficult. It says the random variable z has probability distribution, and we have the probability distribution table for this particular random variable. So it says the expected value of c is 5 2/3, right? So the first thing I notice is that we need to convert this to a improper fraction, right? If you remember how to do that, it's basically we multiply this times this and we add the value here. So 3 times 5, that's 15. 15 plus 2, that's 17 over 3. So this is the same as saying 17/3. Okay, so we have the value of the expected value, and we want to find the values of x and y. Okay, how can we do this? The first thing we can do is use the concept of expected value, right? We know that the expected value, that in this case is 17 over 3, is found by multiplying each of the possible events by their probabilities, right? So 17 over 13 is equal to 2 times 1 over 6 plus 3 times 1 over 6 plus 5 times 1 over 6 plus 7x, right? 7x plus 11y. Okay, if we simplify this, we would get, let's do a step-by-step process. This would be 2 over 6, 2 over 6, which is 1/3, right? Plus 3 over 6, which is a half, 1 over 2. Plus 5 over 6, we cannot simplify that. Plus 7x plus 11y. Okay, if we keep on simplifying this, if we add up all of this, we would get, this is 17 over 3 equals, this is 10 over 6. Maybe it's better if I leave it, just to avoid confusion, I will leave it as over 6 here. This is 2 over 6, and this is 3 over 6. So it's easier to add up these terms, right? 2 plus 3, that's 5. 5 plus 5, that's 10. So 10 over 6 plus 7x plus 11y. Okay, now I can simplify this. If I simplify this, this is 17 over 3 equals 5/3 plus 7x plus 11y. So then if I take this term subtracting to the other side, it will be 17 minus 5, which is 12. So 12 over 3 is equal to 7x plus 11y. 12 over 3, that's 4. 4 is equal to 7x plus 11y. Okay, so here we have our first equation, right? We have two variables here, x and y. So we cannot solve this yet. So I'm going to call this equation number 1. Okay, where can I take my second equation in order to solve this? If you remember from the previous class, we know that the sum of all of the probabilities must always be equal to 1. So that's exactly what our second equation would be about. So I would say that the sum of the probabilities must be equal to 1, right? So I'm going to apply the concept here and say that 1 over 6 plus 1 over 6 plus 1 over 6 plus x plus y should be equal to 1. And then I need to solve this. This is 3 over 6, which is a half. 1/2 plus x plus y is equal to 1. So here I can say that x plus y is equal to 1/2. 1/2. And this would be my second equation, equation number 2. I have two equations and two variables, x and y, so I can solve this system. One way to solve this, if we're not using calculator, is, for example, let me see. I'm going to write both equations, one on top of the other. I'm going to do that right here. I'm going to use this space here. So I'm going to write both equations. In the first equation is 7x plus 11y equals 4. And the other is x plus y, I'm going to write it in order, is equal to 1/2. I'm going to write it as 0.5, same thing. Okay, so one thing I see I can do here is, for example, I can multiply the second expression by 7 in order to be able to simplify the value of x, right? So if I rewrite this, I'm going to write again one on top of the other. This is equal to 4. 7, so here I have 7x plus 7y is equal to 0.5 times 7, that's 3.5. Okay, so then if I subtract, I'm going to subtract this 2, so the x's will eliminate by. So we're going to get 11 minus 7, that's 4y, and this is equal to 0.5. 4 minus 3.5, 0.5. So then I can get the value of y. Y is equal to 0.5 divided by 4, and 0.5 divided by 4 is 1/2 divided by 4, 1 over 8. Okay, so there we get the value of y, our first answer, the value of y, and now I need to get the value of x. In order to get the value of x, I can replace it in either of the two equations I wrote here. It's easier to do it in this one because it's almost, the x is almost alone already there. So if I go to the second equation, I would say that x plus 1 over 8 is equal to 1/2, right? 0.5. So then I can solve for x and say that x is equal to 1/2 minus 1 over 8. And if you subtract this, this would be equal to 1/2 minus 1 over 8. That's 3 over 8. Okay? And this is the value of x. So that's how we solve this type of exercise. See that it's only one extra concept that we introduced, which is the expected value of a random variable. Okay, so I hope this was clear. If not, please let me know. We're gonna practice with this in future live sessions. See you.